Hi everybody, this is the lecture for chapter 21, carboxylic acid derivatives. Alright, so we have talked about this many times, and essentially what a carboxylic acid derivative is a compound that can be converted to a carboxylic acid by a simple acidic or basic hydrolysis. So those functional groups include acid halides, anhydrides, esters, amides, and nitriles. Okay, so let's look at the nomenclature for some of these functional groups. So we'll start with esters. We can imagine that esters are synthesized from an alcohol and a carboxylic acid. And so it's helpful to think of this reaction or think of an ester as being composed of two halves like this, because that's the way the IUPAC naming works. You have the piece of the ester that contains the carbonyl and the piece of the ester that contains what you might think of the alkoxide branch that's on the other side. And so when we name these, we name the branch first, the piece that doesn't include the carbonyl, and then we name the carbonyl part is the base of the name. So for example, if we look at this top example here, we can imagine that the ester on the right, ethyl ethanoate, is composed of ethanol and ethanoic acid, and we combine these together in a condensation reaction and we get an ester. And so the carboxylic acid that we would use in this example would be ethanoic acid, right? If we look at the ester on the right, the piece with the carbonyl is composed of two carbons. And so if we imagine that came from a carboxylic acid, then the carboxylic acid would be called ethanoic acid. And then if we look at the other piece of the ester, which is the piece that doesn't contain the carbonyl, it's in blue here, we can see if we imagine that half had come from an alcohol, the alcohol that it would have come from would be ethanol. So we imagine that these names, ethanol and ethanoic acid, the ethanoic acid is going to become the base of the ester. So we're going to lose the IC acid, the ic acid, and we're going to add ATE. So ethanoic acid becomes ethanoate, and that becomes the base of the compound. And then we'll look at the other piece, the ethanol, and the ethanol is composed of two carbons, and so we're just going to retain that two carbon piece. So we're going to basically just count the number of carbons in that alcohol chain. So we'll call that piece ethyl. So the ester then is composed of two halves, ethyl and ethanoate in this case. So if we look at some of these others here, the first example, we have an H on one side. And so that's kind of, traditionally we've seen that as being an aldehyde. And so we can have an H on one side of an ester and it's still an ester. And so that first example, the way that we would name that piece is that if we look at the example above, we see that piece containing the carbonyl had two carbons. Well, this example with the H on one side of the carbonyl only has one carbon, because it would be the aldehyde carbon, right? So if we would call a derivative that has one carbon has a prefix meth, so if that were a carboxylic acid, it would be methanoic acid. And so in the same way that we did above, we drop the IC acid and we add ATE. So methanoic acid would become methanoate, and that would be the name of the half that contains the carbonyl. And we look at the other half, and on the other half we have basically an isopropyl group, right? But remember, isopropyl is not IUPAC nomenclature. So when we have an isopropyl like that, we have to name the branch. It would be a branched branch. So remember, the way that we do that is by referring to the longest chain, which would be ethyl in this case, and there's a methyl branch, so it would be a methyl-ethyl group. If we were using the common name, it would be isopropyl. So in the IUPAC, we have two halves, right? We have the 1-methyl ethyl on the left side, and then the piece containing the carbonyl is the methanoate. So 1-methyl ethyl methanoate. So notice here that generally when we look at most IUPAC names for most functional groups, it's all one long word without any spaces in between. There's dashes in between the different substituents, but there's not spaces. But in the case of esters, we do have a space here, right? Just like in the case of carboxylic acids, because they always have acid at the end, and there's a space acid. Well, in the case of esters, we always have the space in between the piece that doesn't contain the carbonyl, and then a space, and then the piece that does contain the carbonyl. So if we look at the next example, notice that the piece that doesn't contain the carbonyl, if we ignore the oxygen, it's just a benzene ring, right? And we've seen that that substituent before is called phenyl. And if we look at the other side, it's a carbonyl that also has a benzene ring. And if we imagine that piece as being a carboxylic acid, we would call it benzoic acid. And so this becomes benzoate, the half with the carbonyl. So this is phenyl benzoate. If we keep going down the line, we have the half without the carbonyl is just methyl. In this case, it's just one carbon. The half with the carbonyl is it's got a benzene ring, and it also has a spacer in between, right? That benzylic space. And so remember, when we see a benzene ring, it's generally a substituent on a longer chain, especially in this case because that chain contains a carbonyl, then that would take the high priority. So we would count the 2 carbons in the chain with the carbonyl, there's 2 there, and then the benzene would just be a substituent off the second carbon. The carbon with the carbonyl is carbon 1 because it has the highest priority group, and then that CH2 group would be carbon 2, and on carbon 2 there's a phenyl. So we would name this the half without the carbonyl first, methyl, and then we would name the half with the carbonyl 2-phenyl ethanoate. So we just keep looking down the line. This next one, the half without the carbonyl, we've seen this before. Remember, that's the benzylic position when you have that extra CH2 group on a benzene ring. So the IUPAC name for that group, the CH2, when we have a phenyl and the chain is attached to the CH2 at the benzylic position, we call that benzyl. So that half is called benzyl. And the other half, we see that the longest chain has 3 carbons, including the carbonyl. And so that carbonyl carbon becomes carbon 1. On carbon 2, there's a branch, a methyl. And so the chain is propane. If it were an acid, it would be propanoic acid. If it's an ester, it's propanoate. And on carbon 2, we have that methyl branch. So it's 2-methyl propanoate. And so the whole thing, benzyl 2-methyl propanoate. All right, let's look at the next one. We've got a methyl on one half, easy. The other half, remember, when we have a carboxylic acid hanging off of a ring like that, we don't just call it cyclopentanoic acid. In fact, we have to name the entire carboxylic acid at that point because the carboxylic acid isn't really part of the cyclopentane ring. It's hanging off of the cyclopentane ring. So in this case, we would call it cyclopentane carboxylic acid, right? When it's just the acid by itself. So when it is an ester, we call it cyclopentane carboxylate. So just like we did before, we take off the ic acid and we add ATE. So this would be carboxylic acid, and we take off the IC acid and add ATE, and so then it becomes carboxylate. So methyl cyclopentane carboxylate. And then we see the next example has a ring on the half without a carbonyl. So that would be cyclohexanol, right? And so we'll just name that substituent cyclohexyl. And then the other side is just one carbon. So it would be methanoic acid, so it's methanoate. So cyclohexyl methanoate. Here are some amides. So for primary amides, again, we start with the carboxylic acid, and we drop the ic acid or the oic acid or the ilic acid, depending on the specifics of the name, and we add amide, which is just as we had done previously with the ester, right? We start with the carboxylic acid, and then we drop the ic acid, and we add ATE. So here we just add AMIDE, amide. So, for example, cyclopentane carboxylic acid, drop the ic acid. And this, with the amide, we actually drop that YL too. So it's not just ic acid like with the esters. This would be carboxylate, and so we'd keep that YL. With the amide, we drop the YL also. So cyclopentane carboxylic acid becomes cyclopentane carboxamide. Notice that the YLIC, that whole piece is gone, carboxamide. All right, that was for primary amides. Notice though, on an amide, we have that nitrogen, and the nitrogen can have two H's, which would make it an amide, primary amide. It can have one H and one carbon-containing group, which would make it a secondary amide, or it can have two carbon-containing groups, which would make it a tertiary amide. So in all cases, those are amides, and when they're primary amides, we name them in the same way that we would an ester. We just assume that nitrogen-containing piece, we just call it amide, just like we would call it carboxylate or whatever, right? But when we have that an R group on there, we call this an N-substituted amide. So remember, when we're numbering a carbon chain, the way that we deal with substituents is by giving them a number: 2-methyl, 3-propyl. You know, we have to give a number of where the branch is and then name the branch. Well, when the branch is on a nitrogen atom, nitrogen doesn't get a number. We don't number nitrogen atoms in carbon chains. We only number carbon atoms. So whenever we have a branch on nitrogen and we have to indicate that the branch is on nitrogen, we put an N at the beginning of the name. So look down below here now. We've got these are kind of flipped around from when we were looking at esters, but we have the carbonyl half, which in this case is on the left, and then we have the half containing the amine. What was the amine? If we imagine that an amide comes from a carboxylic acid and an amine, so the same way that we did with esters. So in this case, the piece on the left, the carbonyl containing piece, would be ethanoic acid. So notice how the base of this is ethanamide. So we lose the oic acid. So it's not ethanoic acid. It's now ethanamide because we have an amide instead of a carboxylic acid. Now let's name the other half. We have that nitrogen. That nitrogen's always there. That's taken care of in the name amide. When we say ethanamide, we've already named the nitrogen. So we don't need to worry about naming the nitrogen when we name that half of the molecule. It's already been named. We just have to name the branches that are on the nitrogen. In this case, there's one branch on the nitrogen, which is an ethyl. And so instead of calling it 2-ethyl or 3-ethyl, because the nitrogen doesn't have a number, we call it N-ethyl. So this is N-ethyl ethanamide. So let's look at the next one. In the next one, the nitrogen has two branches. They're both methyl groups. And so again, the nitrogen doesn't have a number, but if it did have a number, we would say, for example, 2,2-dimethyl. So we have to do something similar. When there's two branches on the N, we have to say N-N-dimethyl. Because when we say dimethyl, we're saying there are two methyl branches in the molecule. I have to indicate the position of both of them. So I have to say N-N-dimethyl so that when somebody reads that name, they know that both methyl groups are both on nitrogen, N-N. The other half is just one carbon, the half containing the carbonyl. So that would be methanoic acid. So that becomes methanamide. So this is N-N-dimethyl methanamide. All right, let's look at the next one. That one's a big one. It's a doozy. So we've got the half that has the carbonyl. The half with the carbonyl is the half that doesn't have the nitrogen. All right, so that's going to become the base. So we look at the carbonyl, we draw a line between C and N, and we just look at the left half at that point. And so the left half has 1, 2, 3 carbons in a chain, so it's going to be propane. But because it's an amide, it's going to be propan, or if it was a carboxylic acid, we'd call it propanoic acid. And now that it's an amide, we're going to drop the oic acid and add amide. So it would be propanamide, propanoic acid, propanamide. But we've got a methyl group on that branch, right? It's a 3-carbon branch on the left, 1 starting at the carbonyl, 2, 3. But then on carbon 3, why does it say N2? 1, 2, 3. Oh no, sorry. It's a branch on carbon 2. I got confused because of the way it was written. So on carbon 2, there are 2 methyl groups, right? One methyl group on carbon 2 is part of the chain, the propane chain, and one of the methyl groups on carbon 2 is a branch. So when we name that, we would name that half, it would be 2-methyl propanamide. So when we name the other half now, let's look at the other half with the nitrogen. Remember, we've already named the nitrogen because we called it amide. On that nitrogen, I have 2 groups. One is an ethyl group with 2 carbons, and one is a methyl group with 1 carbon. So this is N-ethyl, N-methyl. But I already had a methyl. I already had a 2-methyl. So now I have an N-methyl and a 2-methyl. So the base of this molecule is 2-methyl propanamide, and then the amide part is N-ethyl, N-methyl. So I actually have 2 methyls. One's on the nitrogen and one's on carbon 2. So if we put all this together, it's N-ethyl, N2-dimethyl propanamide. That's a tricky one. All right, nitriles. Remember, nitriles, even though they don't have a carbonyl, that C triple bond N is carbonyl-like in that it undergoes similar reactions. So we include nitriles in this carboxylic acid derivative group. Okay, so when we name nitriles, we just look at the longest carbon chain. And so in this first example, we have 2 carbons, so that's ethane. And then there's a triple bond N to one of those carbons, so that's a nitrile. So we just add nitrile at the end. So this would be ethane, and we add nitrile, ethane nitrile. The next one, we have 4 carbons in a chain. If carbon 1 is the one that's triple bonded to the N, then carbon 3 has a bromine on it. So it's a 4-carbon chain, so it's a butane, 3-bromobutane, and it's a nitrile, so 3-bromobutane nitrile. You just, all one word, no spaces. The nitrile just comes at the end. All right, let's look at the next one. We've got 1, 2, 3, 4, 5, 6 carbons in a row. Carbon 1 is the nitrile, so that makes 2, 3, 4, 5 has a branch on it, and that branch has a methyl group and an oxygen, so we call that methoxy. So it's 5-methoxy. It's a 6-carbon chain, so 5-methoxyhexane, and that's a nitrile at the end, so 5-methoxyhexane nitrile. This is, just to point this out, this one's like aldehyde, which is that aldehydes always occur at carbon 1. They can't come in the middle of a chain. And so in the same way, nitriles are always at carbon 1. They can't come in the middle of a chain. And so we don't have to indicate one nitrile. It's implied that the nitrile is at carbon 1 because it has to be at the end. Okay, let's look at anhydrides. Anhydrides are, we haven't seen much of these yet, but we're going to look at them a bit in this chapter. And so an anhydride is kind of like two esters squished together. You know how on an ester you have a carbonyl and then an oxygen and then some carbon-containing group. Well, in the case of an anhydride, you have a carbonyl and then an oxygen and then another carbonyl. So it's like a carbonyl sandwich. And so these anhydrides we're going to see are fairly reactive because that extra carbonyl group helps with resonance and helps to increase the leaving group ability of that half of the molecule. So let's look at naming them for a minute here. An anhydride, we could cut it in half right at that oxygen atom, right? And so we can look at both sides of the anhydride. And so when we're looking at symmetric anhydrides like this, we only have to name one half essentially, because when they're symmetric, we assume that the other half is the same. So anhydrides don't have to be symmetric. We are not going to look at naming any asymmetric anhydrides, but just recognize that there's no requirement that both halves of the anhydride be the same. But when they are, sure makes naming easier. So let's just look at those. All right, so if we just look at half of the first one, we have 2 carbons. We would call that ethanoic acid. In the case of anhydrides, we just replace acid with anhydride. So ethanoic acid becomes ethanoic anhydride. And again, we assume the other half is the same when they're symmetric. The next, we would call that trifluoroethanoic acid. So now it's trifluoroethanoic anhydride. These next ones are cyclic anhydrides, and sometimes we'll see these cyclic anhydrides like this. Don't worry too much about naming them, but let's at least look at these 2. Benzene 1,2 dicarboxylic anhydride. And so if those were acids, we would call this benzene 1,2 dicarboxylic acid. And so when it's cyclic like this, we don't necessarily mention the cyclic part anywhere in the name. Benzene 1,2 dicarboxylic anhydride, and we assume that because it's an anhydride and it's connected to carbons 1 and 2, it must also be connected at the oxygen, because that's what an anhydride is. We look at the next one. We have this carbon. This would be 1, 2, 3, 4 if we look at the number of carbons in this chain. And so this would be a butane, but it has a double bond, so this would be butene. The double bond's at carbon 2, so it's but2ene. And now, if we had carboxylic acids at the end, we'd call this but2ene dioic acid, right? We only say the carboxylic part if it's hanging off the end of a ring, not if it were inside the ring like this. And so in this case, because it's an anhydride now, we call it but2ene dioic anhydride. And again, because of the nature of anhydrides being that they are always attached to that oxygen, we don't necessarily call this cyclic anywhere. Usually we have that cyclic prefix somewhere in the word if we're looking at a cyclic compound, but we don't with anhydrides. They don't necessarily need to have that cyclic part in there. So again, just focus for the most part, if you understand ethanoic anhydride, trifluoroethanoic anhydride, symmetric simple anhydrides like the first 2 on the left, you're going to be just fine. All right, phew, that's a lot of nomenclature. Let's move on and look at some properties of these carboxylic acid derivatives. First and foremost, they differ in the groups that are on either side of the carbonyl, or in the case of nitriles, it's not even a carbonyl at all, right? And so those differ in their polarity, and they sometimes use nitriles as solvents. We sometimes use amides as solvents. These make good solvents. They're fairly stable. They're fairly polar. In the case of amides, they have really high boiling points, which can be really helpful for some reactions. So notice here the trend in the boiling point, the increase in boiling point here. We start with butane at a boiling point of 0, right? It has no electronegative atoms, it has no polarity essentially, or very little, and so it only has dispersion forces, and those dispersion forces are fairly weak, so it has a boiling point of 0. When we add the carbonyl in there and we look at an ester, a carbon-oxygen bond is polar, but it's not particularly polar, especially when they're sandwiched on either side like that in that half of the ester. And so the carbonyl is also polar, and we adding those groups in there increases the polarity, so we go from a boiling point of 0 to a boiling point of 32. When we add the nitrile, that carbon triple bond nitrogen is very polar, that triple bond to the nitrogen, and so that increases the boiling point even more. That's comparable to propanol, if we look at propanol there, which is potentially surprising because propanol has hydrogen bonding, and hydrogen bonding typically increases the boiling point of a compound significantly, and that propane nitrile doesn't have any hydrogen bonding, but it does have a very large dipole moment with that C triple bond N, and so that is responsible for increasing the boiling point. Moving up to the carboxylic acid, now we do have hydrogen bonding on that carboxylic acid, so we can see if we look at the difference between that carboxylic acid and the ester, that's a boiling point difference of 86. That's a really huge difference in boiling point, and those two molecules are isomers, right? All you've done is switch around where the CH3 and the H are on those two molecules. But when we've done that, we have created the ability to hydrogen bond, and so you see that represented in the carboxylic acid's boiling point, which goes up significantly because of that hydrogen bonding. Finally, we get to amides, and amides have nearly twice the boiling point of the equivalent carboxylic acid, which again is fairly surprising. They are capable of hydrogen bonding, but another big component is there's a significant degree of ionization in an amide, and we will see that in the next slide here, and you've seen that in your spectroscopy class, I'm sure, when you looked at amides, and often the carbon-containing groups that are bonded to the nitrogen are not equivalent, even if they're the same molecule, right? So we'll see that there's a high degree of ionization, which really does increase the boiling point a lot. All right, so here, as promised, when we look at amides, we have this ability of the nitrogen atom to donate electrons into the carbonyl. And so this is no different than with esters and anhydrides and carboxylic acids, and any time we have an atom that has a lone pair as one half of the carbonyl compound there, it always has that ability to donate the lone pair of electrons in. However, with the nitrogen, we've seen this effect before, that nitrogens are more electron donating. They are less electronegative, so they hold on to those electrons less tightly, which means they're more available for donation. So when we look at this set of resonance structures above, and we can create a similar set of resonance structures for an ester, let's say, but when we do so with an amide, that structure on the right with the charges, the positive nitrogen and the negative oxygen, is fairly significant contributor to the electronic structure of this molecule. And it's so prevalent, in fact, it's such an important contributor that R prime and R prime in this case that we see that are two groups that are bonded to that nitrogen might not have the same signal in NMR spectroscopy, because we have prevented that rotation, that free rotation around that double bond. And so that is indicative of the fact that this is a more important contributor to the electronic structure in this molecule than, say, for the equivalent ester or carboxylic acid, which have similar resonance structures, but they aren't as important. And so we can see this effect in the boiling point of amides. That's why the boiling point of amides was so high, was if we look down here below, we can see that if indeed we're saying this charged resonance contributor is an important contributor to the electronic structure, then we've just increased the ability of this compound to make strong hydrogen bonds, because now that oxygen is negative and the hydrogen being bonded to the positively charged nitrogen is even more positive. So we have created a very strong hydrogen bonding ability because of this ionized form in the amide. Okay, now we get to their reactivity, which we have alluded to many times, and I talked about this in the last chapter, and so here we go with talking about what we're going to do with these compounds now that we have them. We start with an acid chloride as being the most reactive, and as we go down in the functional groups, we see that the next most reactive group is an anhydride, and then an ester, and then an amide, and then a carboxylate. And we can see that this trend in reactivity follows the trend in the basicity of their leaving groups, right? So the acid chloride, after nucleophilic acyl substitution, the leaving group is a chloride ion, which is very stable and not basic at all. It's a neutral ion. Anhydride, that whole piece that has the carbonyl, that whole piece becomes the leaving group. And so you can imagine that when we have that half as the leaving group, that is a very weak base because there's resonance between the oxygen, the negatively charged oxygen, and the carbonyl there. And so that group is not quite as neutral as chloride. It's not as, it's more basic than chloride, but it's still on par. That's a very good leaving group. We compare that with an ester, for example. An ester also has a negative charge on oxygen, but there's no resonance stabilization. So when that OR leaves as a leaving group, it's a fairly strong base. So it's not a great leaving group, OR minus. When we get to an amide, if we have NH2 minus, that's really a terrible leaving group because NH2 minus is a very strong base. And finally, carboxylate, if that were to leave, it would be O2 minus, which is also a very strong base. And so, as we've seen all along, this trend in the more basic the leaving group is, the more reactive it is, and the less reactive is the derivative from which it came. So we look at these carbonyl derivatives. Acid chlorides are the most reactive because chloride is the least basic, and carboxylates are the least reactive because O2 minus is the most basic. So we can see this increased reactivity in anhydrides, whereas if we attack, we're performing some nucleophilic acyl substitution on amides or esters, we get to this tetrahedral intermediate, and we always get to this tetrahedral intermediate, right? And what's different now, if we draw this tetrahedral intermediate where we attack one of these carbonyl groups with a nucleophile, and we look at what we generate with an anhydride, that structure on the bottom that has an anhydride is similar to an ester in that it's OR, except the R group in this case with the anhydride contains that second carbonyl. And so there is resonance stabilization in this tetrahedral intermediate that there is not when we look at an ester or an amide. Esters and amides are tetrahedral. They have no resonance stabilization. But this anhydride, once we get to that tetrahedral intermediate, it does have resonance stabilization, which increases its reactivity. It lowers the activation energy to generate that intermediate. And also because the leaving group is such a weak base, it also increases how exothermic that final step is. So we'll see the structure again when we look at the step-by-step mechanism of nucleophilic acyl substitution with anhydrides. Okay, again, we've seen this before, and I will again point out its importance, which is to say that carboxylic acids are generally only useful, or I should say that the most useful thing that we can do with a carboxylic acid, unless it's what we were shooting for in our target molecule. If our target molecule contains a carboxylic acid, well, great, then we can make one. But if we're trying to use it as a stepping stone from one functional group to another, the most important thing we can do with carboxylic acids is convert them to acid chlorides using SOCl2, which is called thionyl chloride. So once we have a carboxylic acid, we generally use SOCl2 and convert it to an acid chloride, and from there we can easily access any of these other acid derivatives. So if I need an anhydride or an ester or an amide, the best way for me to get there is to make an acid first, convert it to an acid chloride, and then those reactions are thermodynamically downhill for us to create anhydrides or esters or amides. All right, so here is how we might convert a carboxylic acid to an anhydride. So if we start with an acid chloride, and the group that we are adding to it is a carboxylic acid, we're essentially replacing that Cl group on the acid chloride with the whole carboxylic acid. That's basically how this reaction would go, right? So we've seen how we react acid chlorides before, and usually we're trying to make, for example, let's say a ketone. So what I want to do is replace that Cl with an R group. So I would use some nucleophile that contains the R group I'm looking for, and I would replace Cl with R. Well, in this case, the molecule that's replacing Cl is the whole carboxylic acid. So if I use an acid chloride with a carboxylic acid as my nucleophile, then I'm going to eventually end up with an anhydride, and this is what that mechanism looks like. So we can convert an acid chloride to an anhydride, and this is how we would do it. We start with an acid chloride and our carboxylic acid. So notice how when we were discussing anhydrides in the nomenclature, we were always looking at symmetric anhydrides, where the R groups on either side were the same. They don't have to be, and in this synthesis that we're looking at right here, we can make asymmetric anhydrides. We start with one of the R groups that we want on our acid chloride. That's one of the carbonyls. And we'll start with one of the R groups that we want on our carboxylic acid. So notice how the green is R and the blue is R prime. And if I look at the anhydride that I generate at the end, it has R and R prime as the two halves of the anhydride. So using this strategy, we can make asymmetric anhydrides. So in the mechanism, the first step, we take the carbonyl oxygen and it attacks the carbonyl carbon of the acid chloride. Now this step looks counterintuitive, but remember that if I were to draw a resonance structure of that carboxylic acid, the resonance structure would put a negative charge on the carbonyl oxygen. That indicates that that carbonyl oxygen has a high electron density, which means that it's a stronger nucleophile than the other oxygen, because if I look at the other oxygen in that same resonance structure, it has a positive charge, which means its electrons are tied up. So the carbonyl oxygen is really the best bet to do some nucleophilic attacking here, because it has a negative charge in that resonance structure. And again, we've looked at the electrophilicity of acid chlorides before and pointed out that because that chlorine group is electron withdrawing, it makes that carbonyl carbon very electrophilic. So that carbonyl carbon is a strong electrophile. And so now we've identified the most nucleophilic atom is the oxygen on the acid, the carbonyl oxygen on the carboxylic acid. And the most electrophilic atom is the carbonyl carbon on the acid chloride. Sorry, I needed a drink. I was building the tension for building the suspense for the big finale here. And so after those attack, we generate this tetrahedral intermediate. So this tetrahedral intermediate that we're looking at here, this is the one that we saw on the previous slide, or 2 slides ago, where now that we've generated this tetrahedral intermediate, we have some degree of resonance now that we didn't have before when we were looking at the previous tetrahedral intermediates. So this makes our the tetrahedral intermediate lower energy. This intermediate is a more stable intermediate because of that resonance. So the tetrahedral intermediate is going to collapse and reform the carbonyl, as it always does, and the best leaving group in this case is the chloride. So as it collapses, it kicks out the chloride. Then we have this protonated carbonyl as our next step. And so again, we have to lose a proton, and so something will take that proton, potentially a chloride ion, and then we'll be left with our neutral asymmetric anhydride. Fairly easy mechanism. It's just a typical nucleophilic acyl substitution. It's just that first step is a little bit counterintuitive. All right, conversion of an acid chloride to an ester. How does this one work? I start with an acid chloride, and now on the other side, what I want to replace Cl with is OR, because an ester has an OR there. So I need to start with this OR group, and the equivalent, the neutral equivalent, would be an alcohol, right? I just put an H on it, and I'd have this alcohol group. So to convert an acid chloride to an ester, I need an acid chloride and the equivalent alcohol. And so in a similar fashion, the most nucleophilic atom in the alcohol is the oxygen, which attacks the carbonyl carbon on the acid chloride, which forms our tetrahedral intermediate. Notice this one does not have resonance. The carbonyl reforms in the next step and kicks out the chlorine. And then we have our protonated product, and some base is going to take that protonated product, or excuse me, take the proton off of our protonated ester and leave us with our neutral ester. So notice that the mechanism between these two, conversion of an acid chloride to an anhydride and conversion of an acid chloride to an ester, are basically the same. The only difference was that the anhydride had an unlikely first step because of that carbonyl oxygen attacking the acid chloride. But after that, we form a tetrahedral intermediate. The tetrahedral intermediate collapses. It gives us a protonated product, and we deprotonate the product, and then we're done. So these two mechanisms are the same. This one is also the same, right? We start with an acid chloride. If I want to make an amide, then what I want to replace Cl with is some nitrogen-containing group. So that nitrogen-containing group is an amine, so I use an acid chloride and the appropriate amine. And so we're always going to lose one H from this amine. So we have to start with a secondary amine. This reaction doesn't work with a tertiary amine. So we can start with ammonia, or with a primary amine, or with a secondary amine, but we can't start with a tertiary amine. It needs to lose an H in this mechanism. And just like we've seen in the last two examples, we'll see that here again. So the nitrogen attacks the acid chloride. We form the tetrahedral intermediate. The tetrahedral intermediate collapses and kicks out the chlorine. We get our protonated product, which has an extra proton on the nitrogen. Something removes that extra proton, and we're left with our neutral product, right? So notice how we have to lose an H on that step 3 to generate our neutral product, and so we have to have an H in our amine for this reaction to work. All right, a couple more to go. So now, how can we convert an anhydride to an ester? So notice how all we're doing here is we're showing all the interconversions going downhill. I can turn an acid chloride into an anhydride, into an ester, into an amide. I can turn an anhydride into an ester, into an amide. I can turn an ester into an amide. We're just looking at that hierarchy of reactivity, and we're showing how to convert every higher order functional group into every functional group below it. Okay, so that's what this series of mechanisms is showing us. But I want you to recognize how they are all the same mechanism, and we're just changing the specifics of which groups we're using. But it's always the same steps. Here we go again. We don't have an acid chloride this time, we have an anhydride, but the first step is the same. The alcohol attacks the carbonyl carbon on the anhydride, and it opens the carbonyl. So whether or not this was an acid chloride or an anhydride, it doesn't matter. The mechanism's the same. We generate this tetrahedral intermediate. The tetrahedral intermediate collapses and kicks out the leaving group. In this case, the leaving group is that carboxylate ion. In the previous case, the leaving group was chloride. Otherwise, the mechanism is exactly the same. We just changed the nature of that leaving group. Finally, we get to step 3, which has our protonated product, and some base is going to remove a proton. In this case, the carboxylate that we just lost. It's a weak base, but strong enough to remove that proton. And so then we formed an ester, and we've also, notice, formed a carboxylic acid. When we've cleaved this anhydride, and anhydride is essentially composed of 2 carbonyls. Well, in the course of this mechanism, we've broken the anhydride apart, and we've added an OH group and an R group. And so when we broke the anhydride apart, half of it got the H and half of it got the OR. So we created an ester and a carboxylic acid. But the mechanism, the way that we got there, is exactly the same as if I had started with an acid chloride. The only difference is that we generate that carboxylate leaving group, and so it could potentially serve as a base. Okay, conversion of an anhydride to an amide. So notice, again, exactly the same. The amine attacks the carbonyl carbon, breaks the carbonyl bond. We generate our tetrahedral intermediate. The tetrahedral intermediate collapses, our leaving group leaves. The leaving group deprotonates our protonated product. And then we get our neutral product. Mechanism over. Exactly the same. Okay, last one, I promise. So, if we're converting an ester to an amide, right? The one that's lower in energy than an ester is an amide. So there's only one conversion here, ester to an amide. So, in this mechanism, the amine attacks the carbonyl carbon, breaks the carbonyl oxygen bond. We generate our tetrahedral intermediate. The carbonyl reforms and kicks out the leaving group. The leaving group deprotonates our protonated product, and we're left with our neutral product. Exactly the same as all the other mechanisms. So all these mechanisms, I hope that you noticed that we just went over a bunch of them. We just did 7 mechanisms in a row in like 10 or 15 minutes, but they were all exactly the same mechanism. The only difference is what the specifics of those groups are, but the arrows are doing the exact same thing in every single one of these. The arrows are exactly the same. So there's a lot of mechanisms, but don't get worried. They're all the same. Okay, so I think that's good for today. We'll pick up here on Wednesday. This is a fairly short chapter, actually. We're almost done with this chapter already because we've already seen a lot of this stuff. And so we'll finish up this chapter probably on Wednesday or Friday, and then we'll just start doing some review. We've got a little bit to look at in chapter 22, but we're not going to do the whole chapter. We're just going to look at a couple of things, and then we're done. And then we're just going to use the rest of the time to review for the ACS test. So if you have any questions, please send me an email, and I will see you on Wednesday.